Yep. Okay, now.
All right, Bob Mcgovern is in. That took about 20 minutes.
Unbelievable, yeah.
Well, we got you in. How we doing, everybody?
I think we're doing well. This is Tom. Can you hear me?
I can hear you, Tom.
Okay.
Doing great. Michael's here.
Hey, Michael.
Hi,
Good to see you.
Can you hear me?
It's good to see Andy Chapman. Hey, Andy. I purposely didn't turn on my video. I don't want to clog a lot. If there's a lot of people on, it could be a pain. But Andy, you definitely stay on because we want to see you. We haven't seen you forever.
Because I have this plugged in.
All right.
Because
so
it
let me
works.
look at my presentation. Look at this one.
Are the rest of us supposed to turn off our video thing?
Yes.
If you would, I would prefer that, and then I'll encourage you to turn it on after our talk.
10-4.
But all right.
Okay.
So Michael, you stay on. Michael's the presenter along with me. I'll put my camera on real quick.
Okay.
Hello.
Yeah,
Oh, we lost Andy. I didn't mean to kick Andy out. All right. Andy's all the way from Thailand.
Buddy there.
Oh, you can see. Yeah, but you have it enlarged at the full screen.
That's the one nice thing about being able to remote in.
Yes. Andy, you could have kept your video on. That's all right. Not a big deal. We'll all catch up afterwards. So welcome, everyone. We're having a joint Rochester Academy of Science Astronomy Section, Rochester Academy of Science meeting tonight, virtually. Just a couple things before we get started. I want to thank Dave Pesch and his company for donating this service to us to use this evening. With this service, we're able to get unlimited people for an unlimited amount of time. So I know some of the services you have to pay for, you can get that, but we can do this thanks to Dave Pesch and Expudo. So I want to give a hearty thanks to David and his company Expudo for that. So thank you very much.
Thumbs up on that one.
Yes. So how this is going to work, if it gets noisy, we can mute you, and we will if it starts to get noisy. But I would encourage that if you have your microphone on, great, go ahead and talk and ask questions and whatever, you can interact. But if it starts to get noisy backgrounds, I'll mute you. Don't feel slighted. You can always unmute yourself, so it's not a big deal. Anybody can unmute themselves at any point in time.
Sounds like a threat.
Yeah, it is a threat. And it's best to talk with a headset if you have one, but that's why I have my headset on. So, hi, everybody. So let me introduce Michael Grenier, president of the Rochester Academy of Science. Here's our agenda for tonight. I'm welcoming you now, and then I'm gonna turn this over to Michael. We'll have, as part of the Rochester Academy of Science annual meeting, this is our agenda. We'll have voting elections. We'll talk about the procedure. We have an induction of an astronomy section member as an RAS fellow. We'll announce the results of the election, and we'll welcome new board member that will be present. And then for the astronomy section immediately following, we'll have announcements, and then a virtual talk by Dr. Nick Warner of Geneseo about the Mars InSight rover. So let me turn this over to Dr. Grenier. I think he's that side. Yes.
Okay. Well, first of all, I'm not sure if I'm still muted or unmuted. So can you hear me?
Yes.
We can hear you.
Okay,
Yeah.
great. I'd like to welcome everybody to the 140th annual meeting of the Rochester Academy of Science. Since we were founded in 1881, we've always had an annual meeting. We were undeterred by World War I, by the 1918-1920 Spanish flu pandemic. We met throughout the Great Depression and even throughout World War II. So it gives me joy to welcome you tonight during this challenging year for our annual meeting of our members. Our first order of business is going to be election of officers. Our bylaws call for ballots to be mailed to the secretary, but our practice has always been to also collect ballots in person at section meetings at the annual meeting. Because there have been no gatherings, we are permitted under New York state law to gather additional electronic ballots at a live virtual meeting, and here we are. And the board of directors has approved our doing so. So I'm going to turn it over now to Anthony Golembeck, who, on behalf of our nominating committee and our tellers, to talk about tonight's balloting. Tony, can you take it away?
All right. I promoted Tony to moderator so he can go from here.
Sure. Good evening, everyone. I am the appointed teller this evening, and I will be doing a poll here in a moment. I'm trying to verify where that is.
So it's the blue plus sign down below.
Oh, right. Yep. Got it. Nope.
Oh,
It's not there.
I'll make you the presenter. Now try it.
There we go. There it is. Thank you, Mark.
There you go.
So we're going to do a poll here. It's just a simple yes/no poll. The question is there at the bottom of the screen. Do you, as a member of RAS who has not voted yet, approve the slate of nominees? And so now you should be getting that poll.
Yep, that'll appear in your lower right-hand side of your screen. If you're a member, please vote. If you're not a member, please don't vote.
If you voted by paper ballot already, don't vote again.
And so, Tony, I see 46 people here. Not all of us, all these people might be members. They might have some guests here. So let me know when you think you're close to a quorum of votes, and we'll move on.
I believe we've made quorum. So, yes.
All right. So we'll announce that in a second, but let's go on to the next order of business then. I'm going to take this away from you, okay?
One moment.
I just took it from you. You want to give it when you need it back?
I think
Hang on, I'll get it back.
I think
Okay,
we're good.
all right.
I think I got it in my buffer here.
Okay.
Yes, I did. All right.
All right. So tonight, I'll turn this back over to Michael Grenier.
Yeah, so I want to talk about fellows and fellowships. Our Fellows of the Academy were established in 1889. It was our 9th year of being the RAS, to recognize members at that time who were professional scientists. Outstanding service to the Academy. In 1946, fellowships were redefined to be our highest honor and were made a lot more rare. Our criteria include significant contributions to one or more sections or to the Academy as a whole, and either significant scientific work and publications or significant communications in the presentation of science. This year, it is our great pleasure to induct Robert Mcgovern into a fellowship in our Academy. Many people have worked on this on Robert's behalf, and here to read the citation for Robert is ASRAS President Mark Minerich. Back to you, Mark.
Thanks, Michael. I have a special picture I composed for Bob Mcgovern. It's kind of a combination. That's Bob with a bobblehead. And behind Bob is an image that he did about 2 or 3 years ago of the sun. I colorized it so it'd be a little prettier. That he did of a sunspot group on the sun, which he is known for. So with that, I'll read his citation. So Bob Mcgovern joined the astronomy section of the Rochester Academy of Science in 1998, and since 2005 has served the Academy as the appointed position of site manager for the Marion and Max Ferris Center for Observational Astronomy. Bob's tenure is marked by expanded facilities, an active year-round program. He has been the general contractor, master craftsman, and labor foreman for most of the structures on the grounds. Among the buildings projects he's done are a garage, several observatories, the major renovations of the classroom building. The Ken and Trudy Brown Memorial Deck that he added has become a well-used and favorite gathering place for members. Bob is the Ferris Center's biggest fan and promoter, using the facilities to enrich public awareness and understanding of science. He schedules and hosts monthly open houses, holding the September event in conjunction with the Ionia Fall Festival. He plans events that are child-friendly, such as Halloween parties, winter sledding, and Rochester Starfest activities that include fossil digs, birdhouse buildings, and his infamous potato cannon. Bob's participation in section education programs is exemplified by his leadership in our summer science camp. He shares his knowledge on diverse topics such as including plate tectonics, constellation mythology, Avogadro's number, Archimedes' principle, and aerodynamics. A child at heart, Bob's playfulness and enthusiasm leads to performing exciting experiments and demonstrations that engage the scientific curiosity of young people. Study of the sun is a personal passion for Bob. His solar images are fully documented with interesting solar details, image capture techniques, and wavelengths. His solar work led Al Urles to work with the Farish Foundation to fund construction of a dedicated solar observatory at the Farish Center. Bob uses this financial gift to create an observatory for a state-of-the-art solar telescope setup. He promoted the introduction of internet access, making it possible for members to transmit live views of the Mercury transit in 2016 and 2017 solar eclipse. Bob dreams of the day when real-time remote viewing will be available on demand. In recognition of these outstanding contributions, we welcome Robert J. Mcgovern as a Fellow of the Rochester Academy of Science. And this is signed by President Michael Grenier and Secretary Helen D. Haller. Congratulations, Bob.
Thank you, Mark.
Academy Fellow and past President Yuta Dudley, Dr. Yuta Dudley, with a few words of welcome for you.
Hi, Bob. As a board member and a fellow of the Academy, I'd like to welcome you as a new fellow of the Rochester Academy of Science. Your extraordinary service is remarkable, and we are pleased to formally honor you tonight. I can hear a lot of virtual clapping and real clapping out there, so thank you very much.
Yay!
Congratulations, Bob.
Thank you, Mark and Yuta. Can you hear me, Mark?
I can hear you fine.
Yeah, we can hear you.
Okay. Well, I'd like to thank Frank Bowe for initiating this award, and to the Academy Board for its approval. A big thanks to the numerous boards of the astronomy section for supporting all of the projects that I was involved in for the past 17 years. I enjoy spending money. To Max Farish and to Louis Wolk as great charitable individuals who helped in the financing of many of these efforts, facilitated, of course, by our champion, Dr. Al Urles. To the special group of members who over that period of time participated in the numerous construction and work parties, many close friendships were formed during that time. To my wife, Anne, for her understanding. I hope to be able to continue helping out at the observatory and continue my observing there for the foreseeable future. Thank you, and I really appreciate the citation.
You're welcome.
Thanks, Bob. Thanks for all you do. All right, with that, we'll go to the election results. So, Tony, what do we have?
We have a unanimous decision. The slate was approved both from the 11 paper ballots and the 33 votes virtually. And
Fantastic.
I hand that over to our president. If I don't know if you wanted to say anything about that.
Just a few things. I'd like to congratulate our board members and officers who are willing to give us yet another year of service to the Academy. And thank you all for showing your support for these people. And I'd particularly like to recognize a new member of the board of directors, Dr. Michael Richmond, professor of physics and at the Rochester Institute of Technology. Teaches physics and astronomy at RIT, runs the observatory, does a host of other things, and he is admirably suited to be a board member for the Rochester Academy of Science. So welcome, Dr. Richmond. Thank you very much. I appreciate your joining us. And with that, Mark, I'll turn it back to you, and let's go into an ASRAS meeting.
Sounds good to me. Sounds good to me. Congratulations, Dr. Richmond. All right, so welcome. I'll have a few announcements, and then we'll go into our talk with Dr. Warner, who I expect to come on in about 15 minutes or so. So this actually went a lot faster than I expected. So, any observing recently? Feel free to talk. I know there's been a lot to observe. Comment.
Well, I managed to see Saturn the other night, beautiful ring around it, and also all 4 moons of Jupiter. And this is about 3:30, 4 o'clock in the morning.
Yeah, and Jupiter's and Saturn are rising earlier now. You can actually see them earlier and earlier in the evening. We'll actually not have to stay up that late to see them.
That's right.
I'm going to put a quick poll up. How many people have seen the poll? Have you seen the Comet Neowise? How many people have seen it? Just a quick count to see how many people. We have 47 people here. So I'll do a quick poll. Just answer yes or no if you've seen the comet. I'm just curious. So the picture you see here is from Nick Lamondola, and I actually put a whole slideshow, a movie, if you will, at the beginning of this. If you want to see it again, I could show it at the end of the meeting. It's got to be 30 some odd images that our members have taken of Comet Neowise. It really is a beautiful comet. So the results I have so far are about 50% of people have seen it, and 29% have not seen it. The rest have not responded. So that's quite a few people.
It should be pretty good tonight.
It's supposed to be good tonight. All right. Any other observing before I move on? So Dr. Richmond says on Tuesday morning, easier for me to say. Asteroid 256 Anna did not occult the star TYC 1181-6511. The shadow just missed us. Yeah. And it's cool to see a star get occulted. I actually was working with Brad Timerson on one a few years ago. It's kind of cool to see that. Any other imaging? All right, move on. So here's some announcements. This is actually a repeat announcement, but it's appropriate because we're going to try to gather tomorrow, and that we have tick and Lyme disease info and notices all over the place. So there's signs all over the place near where you might find ticks, and then on the table in the Wolk building are all kinds of brochures about ticks, how to avoid ticks, how to remove a tick if you happen to get one, and what to do if you do get bitten by a tick. So please feel free to take any of that literature. We have a whole box full of that stuff to refill if we need to. So, but just beware, there are ticks out there. You probably won't encounter a tick if you stay in the mowed grass. They tend to stay in the higher level grasses and near the trees and such. So if you wander off into the woods, that's when you got that's when you have issues. All right. So we are, I'm in the process right now. I'm working with David Bradley to actually do one of the things that was on Bob's list of things to do to virtually broadcast observing. And we're in process. So Dave and I have had 4 sessions at the Big Dome with the C-14, recording short photos through that telescope. And then we originally tried to stream it, and with my narration of what we're looking at, and describing the object, where it is, what it is, and how it forms, all kinds of things about the deep sky object. And streaming did not work. We have a very slow connection, so it was very choppy. So between getting nights that are clear and we could do this, we tried to record it. I'm happy to say that on Wednesday night, we were able to, with Bob Mcgovern and Dave and I, were able to record a bunch of stuff. And so I'm in the process of putting that all together. We'll have a virtual observing session that I will invite you to. So let me ask you guys, would you guys like to have a meeting like this to do a virtual observing session, or you want me to just upload it onto YouTube and you can do it on your own? What do you guys think? Feel free to unmute yourself to make a comment.
Yes, I think it'll be great.
Do you think we should have a meeting like this?
Yes.
And then gather together to view it? We can actually answer questions as we go in the chat, an interactive virtual session, Mary says.
Actually, I'd like to see what the rest of the program's like before I can answer that.
Well, if we do it like this, then you'll have a lot of other people around to interact with as it happens versus just watching it by yourself. Andy says he would join it. All right. If we can get people on the other side of the world to join it, it must be good, or it must be worth a shot anyway. All right, so I will stay tuned. I'll send out a note, a lot like we do for these meetings, for another meeting that we'll do a virtual observing session, and we can actually record that and release that as a video that way. All right. Yeah, Chris, it's very similar to this kind of meeting. All right, so stay tuned. Like I said, I got a bunch of video recorded. I have at least an hour's worth of session to do. It might be even more. So maybe I'll make it into a couple sessions. So should be fun. Yeah, Michael likes it with others. All right. All right, it's decided. We will do a meeting like this. Cool. I'm excited to do it. All right, so here's a big announcement. So tomorrow, we're going to have the first member observing we've had in a very long time. So we're going to ask a couple of things of you. If you're going to come out to observe, please bring your own equipment or bring your own eyepieces. We don't want to share eyepieces between people, just for safety's sake. So when you come in the building will be a clipboard, and we'd like you to sign in your name and phone number that you're here. We need to do that in case we need to trace contacts if we get an active case of the coronavirus. So we know who is here, who else might have been exposed. You do need to sign in. We will have wipes and hand sanitizer available right at the sign-in sheet to clean your hands and the pen and all that stuff. There's more coming on that stuff. So please ensure there's 6 foot distance between people. If you're less than 6 feet apart, you need to wear a face covering, a mask over your face like you've done when you go into the grocery store, go shopping, or anything else when you're interacting with people. If you're by your scope by yourself, feel free to take your mask off. If you're away from other people, you can have your mask off. But if you're interacting with other people, please keep your mask on. The building must be under 50% of a maximum capacity. And I put XX there because I forgot to look. I was just there and I forgot to look to see what the capacity is. Bob Mcgovern, are you still on?
Yes.
Do you know what the capacity of the Wolf building is?
The Wolf building?
Yeah. Is there a? I know it's on a
60
it's on a
people.
sign somewhere in there.
I would say
people,
sorry.
6 to 7 people, maybe.
No, in the Wolf.
It says 60 on the wall.
60? Right.
Yes, because you've gone
David
over
says
that
it's
many
60.
times.
Okay, so we want to have no more than 30 people in there at one time, which I think is pretty safe for an observing session. Might be different if we have a bigger event going on there. Okay, and then in each of the buildings, no more than 4 people in the cave roll off or the Wolk, the 20-inch roll off. You can't have more than 4 people in there. Both bathrooms will be cleaned. I'll be going there early tomorrow to clean both bathrooms, so they will be sanitized. And in the bathrooms will be wipes to wipe the handles in your hands. I would ask that these rules will be posted on the bathroom doors and inside the bathrooms, that you wipe the faucet and hands with the disinfecting wipes before and after you use the bathroom. If you use the toilet seat, please wipe it, or if you handle it, wipe the handle down before and after use. And then dispose of the wipes in the trash cans that are there. Please don't flush them. We're on a septic system. It's not wouldn't be encouraged for our system to do that. So if you could put them in the garbage can, that would be good. And then wash your hands. I would also ask, this is a star party, so please use your red lights. Please bring red lights. If you don't have a red light, we have a limited supply of them inside the library to walk around and see what's going on. If there's a number of people there, you probably won't even need a flashlight. You'll be able to walk around if you're just going to be socializing. But especially after dark, just use red lights and then have a good time. Is there any questions or any other concerns I can answer for this? Okay. All right, and we will have a meeting in August well, I would love to have it at the Fair Center, but it sounds like we're going to have another virtual meeting via this same venue. It's the current and future space projects at L3 Harris. And Dave, do you have an update on the speaker yet? I know you've arranged the speaker. You're arranging that speaker. I don't know if you have that person lined up.
I have arranged a speaker. It's 2 different people who are talking about doing it, and neither one has given me a response yet. Just that they will do it.
All right.
I work at L3 Harris, and I was amazed when I saw this presentation, guys.
Well, we are sitting on our hands waiting to see this. It sounds like it'll be interesting. So Mary asked about site eyepieces, and no, we won't be using the site eyepieces. You should bring your own eyepieces with you. All right. Then we have a board meeting the following week. That's on a Wednesday. We've been meeting on Wednesdays for a while now, and it is earlier. If you want to join us, let me know. I'll send you the link to the board meeting. When you logged in tonight, you probably saw that there was like a board section there, so you can log into that section, and there's a code that you use to get into the board meeting. Let me know if you want to come in, and I'm glad to provide you with the link and the password to get in. So please come if you're interested. We are meeting an hour earlier because that night is also the Perseid meteor shower. So I would encourage you, if you're able to get out this weekend, or if you want to come out for the Perseid meteor shower, it'll be the same set of rules, and I'll release those again when we get closer to the Perseid meteor shower to watch that shower. The peak night is the 12th of August. So everybody's welcome to attend. Anybody's welcome to attend the Perseid shower, and any member that wants to visit the board meeting, just let me know. Any questions about that event? There's actually 2 events. Okay. Well, Nick's not on yet, so we have time to mess around a little bit. I told Nick he didn't have to come on until about 8 o'clock, so we were much faster than I expected. So I'll tell you what, I'm going to put up the video of hang on. Bear with me here. The video of our this was our image show. If you want to make comments or questions about these pictures, this was Dave Bradley from the C14. I think this was Monday night or Tuesday night this week. Is Dan on? This might be behind Dan Kuchta's house. Sent this out earlier this week. I'm just amazed at the number of images we got. There's Brian Oyer somewhere over the skies in Greece, maybe over Lake Ontario. And Joe Altieri's got a whole bunch of images he's done over Lake Ontario. And then I think there's a spectacular one over Letchworth Park.
So approximately how long does it take for one of these to come into view and go out of view?
For the comet,
Yes,
depends on where you are, where the horizon is.
yeah.
It's not visible till about 9 something at night, and then it's only visible till it sets.
Oh, that takes what?
It doesn't
How
take long. When I was at the Ferris Center, the trees were in the way. When I took this image, the trees were in the way by 10:30. I couldn't see it anymore because the trees were there. Now I may have had a little bit longer time if we didn't have all those trees there. All right, I see Nick's here. So we'll finish this video up, and Nick, we're ready for your presentation whenever you're ready. So if you have you want to get your presentation ready, I'll make you the presenter.
You got
in
it.
a couple of minutes here.
Okay.
Thanks, Nick.
Yep.
I'll introduce you as soon as we're done here. So Brian Oyer did a nice job here of showing the separation between Merak and Dubhe being about 5 degrees, and then look at the comet was a little more than 5 degrees in its tail. That's pretty cool. So I would encourage you. It's visible in the evening. You don't have to get up at the crack of dawn. You can just stay up till a little after 10 o'clock, and you can definitely see the comet in the northwest. It's best with binoculars, and in some places you can actually see it naked eye. But I needed binoculars to find it, and then I could kind of see it naked eye. That's been my experience. Anybody have different experience seeing the comet?
Yeah, Mark, once I had used the Big Dipper to zero in on the area with averted vision, I was able to pick up a few minutes after 10 o'clock Wednesday. I had maybe half an hour before it sank into the haze.
How was your northwest view from there? Did you have trees up there, Steve?
Well, I framed it between two trees.
Okay.
So I was able to sit the next door neighbor down and say it's right in that gap. And he was able to see it too. But it's
cool.
Not a lot of contrast with the sky.
No, definitely not. So Nick, are you on? You have your microphone on, Nick?
Yep, I'm here. Do you hear me? Do you hear me okay?
Yeah. One second. There's another Nick.
Oh, another Nick. Yeah. Sorry about that. Okay.
It's okay. But you will be up shortly. Nick Lamandola, do you have your microphone on? He doesn't.
Yes, Mike. Yes, Mark.
Oh. How many mornings did you get up to image this comet?
Mornings, 2.
2?
Evenings,
okay.
3.
Okay. I know you had at least 4 or 5 times out there, so I didn't know if it was all mornings or all evenings or what. So I want
to maybe 3 more. 3 mornings, Mark.
Right.
I'm sorry, 3 mornings.
Yeah. You get the endurance award.
It's worth it.
It is worth it. It is. How often does this happen? I mean, the last beautiful comet like this was probably in the 90s, right? 97, 96, 97. And that's one of my favorites.
I saw Hale-Bopp.
I saw Hale-Bopp.
But I never imaged it.
Yeah. And this last one is my favorite. This is the one that Joe Altieri did over Letchworth Park. That was pretty cool. Great contrast between the gorge and the comet and the trees there. So, all right. Well, thanks for engaging me here. I'm going to now, Nick. I'm going to turn this over to you. Make you the presenter. If I can find you in here.
And I can share my webcam as well.
All right, please do.
My face.
I am making you the presenter.
There we go. I'm going to start sharing. There, you see me? Hi, everyone.
Now we see you.
Excellent. Okay, so I'm gonna do the share screen option here. So give me 1 sec. Let's see. Select entire screen, allow. There we go. I'll just take a second. Oh, you're seeing that. Okay, hold on a sec. There we go.
You're better off sharing the presentation. There you go.
There we go. How's that look? Is that okay?
It's a little chopped top and bottom.
Yeah, so what I noticed about that when I tested this earlier is it chops it off. There's a, you'll notice there's a make screen share full screen option next to my presentation. You might not see my face then.
Oh, I see what you're saying.
Yeah. Otherwise, when I shared just the PowerPoint, for some reason it showed my slide list on the left, which is fine too. It's not that big a deal.
What we could do is encourage everyone to take your picture and you could drag it down maybe in the corner and that way you can see the whole presentation.
Yeah, exactly. You gotta move you gotta move that overlay so it doesn't cut off the top screen.
Yeah.
Okay, so
okay. Very good.
All right. Cool. All right. Well, thanks for inviting me. When we originally planned this, it was going to be outside, I think, somewhere a long time ago. But I'm glad to be here anyway, and got some pretty cool stuff to talk about. Now, I'm from Geneseo, SUNY Geneseo. I'm in the Department of Geological Sciences, and I'm also a participating scientist on the InSight mission, which is the subject of the talk today. Now, what's kind of cool about this is I think I gave a talk to you guys, 6 years ago? And at that time, the talk was all about trying to select an appropriate landing site for this mission. And I went through all the processes and everything that we did. And it's really exciting to be able to actually say that all of that worked. We landed perfectly. Everything went awesome. And the mission is currently in the monitoring phase. So what this talk is going to do, I'm going to sort of highlight what this mission is about because not everyone maybe is following it. Give you sort of the science justification first. Talk a tiny bit about the landing site, but then get into mostly at the end some results with some of the pictures. Okay. So for those of you who don't know, this is the picture of InSight taken by its deployment arm immediately after landing with the solar panels unfurled, and it's just gorgeous. I'll talk more about the cameras themselves. But the InSight mission stands for Interior Exploration using Seismic Investigations, Geodesy, and Heat Transport. Do you guys see my cursor, by the way? I just want to make sure that that's visible. Excellent, because I'll use that kind of as a pointer. So the whole point of InSight is to understand the interior structure of all the terrestrial planets, the 4 rocky planets, Mercury, Venus, Earth, Mars, and even the Moon. And we only really have a really good data point about the interior structure of Earth. We have some data from the Moon, from Apollo, but we don't have any of this data really from other planets. So that's kind of the goal of the mission, is to look inward to planets. It has been operating for 1 Mars year, and it's a static lander, so it doesn't move around. Right now we're actually so 1 Mars year, about 2 Earth years. So right now we're about 1.5 Earth years into the mission, and everything is going really well. There's a couple weird things going on that I'll tell you about towards the end. That's the what's called the nominal mission. That's the mission that NASA has fronted money to fund. So we're getting very close now to where we're going to be submitting a extended mission proposal because the spacecraft is still healthy. And as long as it's still healthy, we want to keep monitoring what we're monitoring. So talk about that more. It launched in May of 2018. It launched off the West Coast at Vandenberg, and it landed in November 2018. So again, we're approaching that 2 Earth year threshold right now. So this is just a schematic showing all the different instrumentation on board InSight. There really are 2 primary instruments. First of all, number one, it is solar powered, as obviously you can tell by the large solar arrays. But the 2 primary missions are in this schematic, are deployed on the surface. So to the right of this picture here is the seismometer. Now you can't see the seismometer itself. It's currently covered in this picture by the windshield. The goal of the seismometer is to detect what we call Marsquakes, so essentially earthquakes on Mars. And on the left is the HP cubed, the heat flow and physical properties package. which is designed to penetrate. It's essentially a mole, as we call it, a percussive mole that penetrates into the Martian soil, the regolith, and is going to, and is trying to right now, measure the heat flux of the inside of Mars. So I'm going to talk about the results from both of these instruments. Other important things to note on here, the deployment arm, which is this white arm structure you'll see right here. It's also known as the IDA. This is the thing that picked up the instruments and placed them onto the surface. And you can see the instruments are each detached by these engineering tethers, as they call it. That's where the electronics are. Other instruments on here that are science related, on the arm itself, there is a scoop at the end. There's also a camera. You can see it right here called the instrument deployment camera. It's a color camera. You have another camera called the context camera, which is right here. And it's a fisheye lens camera that's just underneath the deck. So you'll see pictures from both the IDC and the ICC in this presentation. And then there's two wind sensors called the twins that can get wind velocity and direction. There's a pressure sensor to detect atmospheric pressure. So this is actually the most sophisticated weather station ever put on Mars. And then there's a series of antennas which are designed to track the precise rotation rate of Mars, but also to try to determine the wobble of Mars, essentially, as it rotates around its axes. And that'll help you to give some constraints on what the core is like of the planet as well. So it's very much a geophysics-based mission looking at the interior. This is a picture from Lockheed Martin when it was being constructed. This is back in 2015-ish, somewhere around there. And I just want to show it because you can see the scale of these massive solar panels relative to people here, just to give you a sense of how big this is. And there's the windshield that's sitting up on the deck here in the white. Then this copper-colored thing is the seismometer itself. And then you can barely see it, but this black structure here is the heat flow probe right there. Okay. All right. I'm going to talk a little bit about each of the primary instruments here. So the goal of the seismometer, of course, the SEIS as it's called, is to detect Mars quakes. It's an incredibly sensitive seismometer. I'm going to talk about how seismometers work a little bit in a second, but essentially it can detect vibrations at the scale of a hydrogen atom. It had to be very sensitive because it has to be able to detect very small quakes as they travel through the crust of Mars. The windshield, as you see in the lower right here, is designed then to prevent wind, which there is wind on Mars, from actually shaking the seismometer and causing all manner of noise. And that's been very effective, the windshield, so far. So the question is, why do we want to know something about quakes on another planet? This is just a very introductory sort of geology sort of idea here. I teach intro geology at Geneseo as well as planetary science. But essentially, think about inside that seismometer, there's a tight spring like you're seeing here attached to some mass. And then when the shock waves from the quake propagate through the crust, they will essentially shake that spring, which again is so sensitive on InSight that it can detect the width of a hydrogen atom. And that shaking will obviously cause a signal, which will be recorded here on the seismograph, which this is old school seismograph here. So you'll see in this little animation, you know, as the waves come through, it'll start to shake and wiggle and create the seismograph, or seismogram, as you see right there. Okay. So we're really concerned about the two different types of shock waves you just saw. The first one that arrived is what's called the P wave, or the compressional wave. That's the first one to arrive at the station. And then the S wave, or the shearing wave, also called the secondary wave, arrives second. And you can use those two waves to essentially say something about magnitude, distance to the epicenter, and all sorts of interesting stuff about the interior of the planet. What they're really trying to do, and I'm not a seismologist, but there's a whole host of the top seismologists in the country, or in the world actually, on this mission, is the ultimate goal of this, after years and years, hopefully, of monitoring of Mars, is to construct a diagram that looks like this. This is my sort of 100-level interior structure of Earth diagram. We have no idea about what this diagram would look like for Mars or for the other planets at all. This was constructed for Earth by looking at earthquakes. So this diagram on the left essentially shows the depth from the surface down to the inner core. And then it shows seismic wave velocity on the x-axis here at the bottom. And you guys probably already know this, but as seismic waves or shock waves move through different materials, they speed up or slow down based on the density and phase of matter. And so the famous example for Earth, of course, is the sudden reduction in P-wave velocity that occurs at our outer core. And that's because our outer core is this liquid iron nickel convecting layer. The S waves, of course, disappear completely and create this giant shadow zone on the other side of the planet where we see no S waves at all. And you can use those kinds of relationships to say something about not only the phase of matter, but the size of the core as well of Earth. So we have no constraints for that for Mars. So what the seismologists are doing right now with the quakes that have been detected is trying to piece this model together. And so that's one of the big stories here. And that'll give us a sense of how do planets organize themselves? How do the terrestrial planets organize themselves and evolve through time? You'll see diagrams like this if you go online that shows different structure of the different planets. A lot of this is based on orbital observations, density measurements, sort of how we've tracked the wobbling of some of the planets on their axes. But none of this comes from direct measurements from geophysical data. So this is all very notional for all of the planets. Except, of course, Earth, we have a pretty good sense, and the Moon, we have a pretty good sense as well. Okay. The other thing that we're interested in is what is the level of seismic activity on the other terrestrial planets? Like how many quakes happen on Mars in the first place? On Earth is an incredibly seismically active planet because we have plate tectonics. The whole lithosphere of the planet is broken up into plates. They pull apart, they slide side to side, they smash into each other. And we're a very seismically active planet, but we're the only terrestrial planet that actually has plates today. Mars may have had plates in the past, but right now Mars is just one single lithosphere. And so we wanted to get a sense of the level of seismicity of other planets as well. And unfortunately, we do have that data now, which is pretty cool. And I'll show that later. If you look at Mars, this is just a picture showing essentially the faults on the planet Mars. So this is a global map, okay, right here. And you'll see the red lines are essentially the faults and fractures that have been mapped by various geoscientists, showing you that while there are fractures and faults, none of them form the pattern that indicate plate tectonics. They don't outline obvious lithospheric plates, although you might argue there are some, like in this area, that might hint at some sort of tectonic province. But overall, this is just one single lithosphere. All you're seeing is evidence of a little bit of stretching and a little bit of compression that's typical of all single lithosphere planets, including the Moon, Mercury, and Mars. You see evidence of just stretching and compression throughout the planet's surface, but no actual plates. Okay, so that's the point of the seismometer, what they're trying to do. Now, the heat flow package is designed to measure the temperature radiating from the core of the planet, the internal heat flux of the planet. And so on the left is the actual structure, the apparatus that's deployed right now on Mars. You'll see this vertical column here is where the mole, as they call it, is actually inside of that little container here. On the right is a zoom in of this mole, and you can see the tip here. It's not a drill, so it doesn't drill down, doesn't auger in to the soil. It's actually a hammer. Inside of it is this little coiled spring that coils up and then releases and hammers down, and that hammering action pushes it down into the dirt or into the soil over time. I have a little video here. Can you guys see my YouTube screen here? Just want to make sure that my screen sharing is working.
Yes, we can see it.
Excellent. Okay, so all I'm trying to show here is what's supposed to happen for this HP cubed. So this is NASA tested the mole. It was actually built in Germany by DLR. NASA tested it in a test bed. The Germans tested it in test beds. This is a container essentially full of sand. They tested it in silt, fine sand, medium sand, coarse sand, gravel, larger particles like pebbles. They tested it in various cemented soils, and in all cases it was successful, although there were various problems throughout. And we'll talk about those problems towards the end here. But just you can see this successful penetration here in this time lapse of the mole going into the test bed. This is what it's supposed to do, and you can see here this tether that's going down with it. All along the tether, there's a series of thermal sensors. So it's not just taking the temperature of the inside of the planet, but it's also giving a temperature profile of the entire soil. Okay, so it just does this basically for a couple minutes. So I can close that. Now, the key here, though, is that it's supposed to get 3 to 5 meters. That's the required depth of penetration. And the reason for that depth is that what we really want is the internal heat from the core. You have to get to that depth in order to see that heat, because shallower than 3 to 5 meters, you have the day-to-day solar flux, essentially, that what we call the diurnal heat flux, which is heating up the soil and causing that signal to dominate. There's also a seasonal flux, which is why we want to actually get below that. If we can get to 5 meters, we can get below the summer-winter cycles in the soil as well. And so that's the target goal. And so in order to, when we were picking the landing site, and I'll talk a little bit about this in a bit, one of the constraints was to find a place on Mars that has a loose, broken up soil, something that the HP cube could actually penetrate through. Okay, so we'll get back to that. Now, why does internal heat matter? Well, we know that Mars had quite a bit of internal heat in the past. There's evidence of these very large shield volcanoes, like this one in the Tharsis province of Mars. This is basically similar to sort of Hawaiian-style volcanoes. These are big basaltic volcanoes. And some of the biggest ones in the solar system, as you guys know, exist on Mars. And they were probably created by these large mantle plumes, so it indicates there was quite a bit of internal heat. But they're all fairly old, anywhere from 4 billion years up to just a billion years ago. Some of these volcanoes were active. There's not a lot of evidence of activity today, and we don't really know what the heat flux is at all today, and if it could still be active in any way. We also don't know how fast the planet lost its heat over time. That's something else we can calculate by getting the internal heat. For me, I'm a surface geologist, what we call a geomorphologist, and I'm very interested in sort of surface processes. And I'm interested in whether Mars was Earth-like in the past, whether it had an atmosphere, whether there was water flowing on the surface. And so we know that volcanism plays a really key role in supplying atmospheres for all the planets, and Earth in particular. The volcanic processes that occurred throughout history have generated the atmosphere that we have today. And if you combine that with the sort of degassing you're seeing here, with our gravity being able to hold the gas in, and also the fact that we have a magnetic field, which I'll talk about in a minute, Earth is able to have a nice, stable atmosphere. So if we think about Mars, if we look at some of the most ancient surfaces on Mars, like this one, I'll come back to the other slide, we see all this evidence that it was once Earth-like. We see evidence of these dry river channels, as you can see in this famous Viking orbiter image from the 70s. These are what we call dendritic river systems. They're tree-branched pattern river systems that are indicative of rainfall over a large, broad area. And so most Mars researchers fully believe that there was rainfall, there was an active hydrologic cycle. There's evidence of deltas, there's evidence of lakes, there may be evidence of oceans and seas, but the fact is that Mars was once more Earth-like about 3.5 billion to 4 billion years ago. Today, if I go back to the previous slide, Mars has an average temperature of about minus 40 degrees to about minus 50 degrees, so it's very cold. But its air pressure is 6.7 millibars. So it's about 3 orders of magnitude lower air pressure than Earth's air pressure, which means it's essentially what this picture shows, like a cold, hyper-arid desert. It's not Earth-like at all today, and liquid water, is not particularly stable at the surface. So in order to get what you see in this picture now, Viking Orbiter, we needed a thicker atmosphere. And to do that, we needed volcanism, we needed internal heat. Okay, so this whole story ties back to sort of the evolution of Mars and its surface. Another final thing to talk about this is that on Earth, our convecting liquid outer core, this sort of rotating, convecting iron-nickel liquid body, generates this strong magnetic field that you see in this artist's picture here on the right. And that magnetic field actually protects our atmosphere from solar wind, basically stripping it away. And we have the 1 bar of atmospheric pressure that's being protected by this. Mars does not have a magnetic field at all today, which is telling us something about the interior structure as it is. But it must have had one in the past, at least for a period of time, to support an atmosphere. Okay, so that's sort of the reasoning behind InSight, is all the things we would like to know about the mission and the reason why NASA funded it in the first place. So I want to take you then to the actual landing itself and then some of the results. I've got another video here, which I just always have to show. That is the artist rendition of the entry, descent, and landing procedure for InSight. So I'm just going to fast forward a little bit to here. If you haven't seen this before, it's just on YouTube. But so there's the spacecraft approaching Mars here. Hopefully you can see that little dot. And I'm going to fast forward and pause on occasion. So I'll pause right here. So this is InSight coming in. There's what we call the back shell of the spacecraft, and underneath is the heat shield. Okay. And it's going to zoom in here in a minute to show you the thrusters. So the thrusters on the spacecraft are designed to do last-minute sort of trajectory correction maneuvers, they're called, to sort of get it to where it's supposed to be on the surface. Okay, so that's those. As it approaches Mars, then it detaches. And because we have that 6.7 millibar atmosphere, that's enough atmosphere to create frictional resistance as InSight enters. And you need this heat shield to basically protect the spacecraft at this point. So there's enough atmosphere to cause this effect. Now at this point, as it enters in, it obviously has to slow down. And so you start by actually using this supersonic parachute, which you can see here, designed to work above the speed of sound. But that's not enough atmosphere. So there's not enough atmosphere on Mars for the parachute to work the whole way. Otherwise, this would be super simple. I'm going to pause it there. This would be a really easy landing on Mars. You just soft land with a parachute. But again, you need something else. And at this point, this is where all the missions have to get creative. How do you get the lander or rover to the ground at this point to decelerate down to essentially a soft landing? And at this point, it's traveling somewhere around 200 miles per hour or something like that. InSight used the cheapest way possible. Because this was not a big flagship mission like Curiosity rover or like Perseverance. This was what's called a Discovery class mission. It was about $400 million. They used the method which is drop it, just let it go, as you'll see here in a minute, and fire the thrusters to basically decelerate it to the surface. Now that's the cheapest way. It's using a radar, of course, to tell where it is relative to the ground. But because of this method, it also results in a very large sort of error in terms of where it's going to land. The probability region of landing is very large, and I'll show that in a minute. So you have to make sure that a very large area on Mars is safe for landing before you send the spacecraft. And of course, the final thing that they had to do, the engineers, is to unfurl the solar panels. If those didn't come open, the mission was dead, even if it landed perfectly. That's pretty cool. Okay. So that's EDL, entry, descent, landing. Now my job, before I got to Geneseo, I spent 3 years at the Jet Propulsion Lab for a postdoc. And when that was going on, InSight was chosen, and my boss was actually, he's the head of this, he's the head geologist of entry, descent, and landing. He's the person who works to select the safe landing sites. And so we spent all of this time looking at orbiting imagery, topography data to try to find a suitable landing site. Now, that was my last talk 6 years ago for you guys. What I want to just say is what we were essentially looking for from space was this surface right here. This picture that you're seeing here is from the Spirit rover, taken in 2004. So Spirit landed in a place called Gusev Crater in 2004. And it landed on this surface, and what you're seeing here is a lava plain. This is basaltic lava, and you can see the dark black rocks here, which are basalt. But it doesn't look like a lava plain. It's not a pristine lava flow like you would see in Hawaii or something. It's all broken up into all sorts of fragments. It's what we call a regolith. It's essentially a soil. This is a 3 billion year old surface that has just been sitting here getting bombarded by meteors over 3 billion years, breaking up the lava into small chunks. Most of what you're seeing here is actually sand size and gravel size material that's just been beaten to heck by meteors over 3 billion years. A little bit of wind has pushed some of that finer material away, but essentially this is the kind of thing we had to land on. It has a gravel sandy soil, so that HP cubed, that probe can get through it. It's also incredibly flat, aside from the Columbia Hills in the distance that you see there, but it's a very flat, safe surface. And the rocks that you see, while they look kind of dangerous, these are like football size to basketball size. So in order for the rocks to be dangerous, they'd have to be about 1 meter to 1.5 meters size before the lander would actually be affected by that. So this is what we were looking for. And so in a minute, I'm going to show you the actual pictures from where we landed at InSight to give you a sense of how we did. This is a picture I showed in the talk 6 years ago, which shows the landing probability region that we mapped out. So this is a geologic map. It's color coded by different terrain units that we mapped using the the orbiting imagery. You see the scale bar at the bottom here, 100 kilometers in size. Here's the latitude and longitude. And this ellipse shape here is the 99% probability of success ellipse. So the highest probability of landing would be right dead center here in the middle of that ellipse. And of course, at the edges here, you have a very low chance, but still a chance to land somewhere at the edge. This is 130 kilometers by 27 kilometers in size. It's huge. And that's because of this sort of cheaper way of landing just based on a parachute and thrusters. Just by comparison, the Perseverance rover, which is about to launch in a few months, its ellipse is only about 10 kilometers wide. So they've improved the uncertainty a lot, and that's a very expensive $2 to $3 billion mission. They're using all sorts of interesting new techniques to land very precisely. This was a very imprecise landing. The green area that you see here is the surface that we mapped that we said was going to be similar to this. So we wanted to land in the green. Okay, so on November 26th in 2018, some of you might have been watching, hopefully live, InSight landed successfully. This is the engineering crew that's in charge of entry descent landing. This individual right here with the glasses is the PI of the mission. He's the head of the entire mission. His name's Bruce Bannard. And Sue Smekar back here, also in glasses, is the co-PI of this mission. Just to give you context of where we landed, this is that same picture without the color map showing the blue areas, the probability landing region, the landing ellipse. As we got closer, the data improved on the velocity of the spacecraft. We knew how fast it was going. We had a better sense of what angle it was going to hit the atmosphere. We had a better sense of what the weather was looking like at the landing site. And so that probability ellipse shrunk to this smaller one, less than 100 kilometers in green. And these dots on here, of course, the green is the center of that ellipse. These dots all have an interesting story, and just for time, I can't go through it all. But if you want to ask me about these dots in the question and answer period, I'd be happy to. But the only dot that really matters is where InSight finally landed, which was the red dot right here. So we landed short, and we landed a little bit north, but still within the ellipse, and definitely within that green unit that I just showed you on the previous map. Okay, so now we'll get into like the landing in the pictures. This is a horrible picture, but it is the first picture taken from InSight, so I've got to show it. This is taken from that context camera that's mounted below the deck. It's a fisheye lens. It's just supposed to look straight ahead all the time. You'll notice all the specs on it here. The dust cover is still on this camera to try to protect it from dust. So it looks pretty bad. But you'll see the horizon out in the distance. And you'll see the foot right here. And trust me, I'll show you better pictures in a minute. But there's the foot of the lander. And there's a rock right in front. And so we were really excited, like some geology to look at. But this rock is, again, only like football size. It's not very big. And if you look off in the distance, you'll see there are very few rocks. This is a really, 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 really flat, smooth, boring place, which is what we wanted. The rocks themselves are kind of dark gray without any visible grains or anything. So these are basaltic rocks. So we did land on a lava plain like we anticipated, just sort of broken up lava plain. So let me show a better picture. So on the left is the landing site, and you can see the beautiful solar panel from InSight. And remember what this looks like, because I'm going to show you what it looks like today. This is at the first day on Mars is what it looked like. On the right is the Gusev Plain. So this is just a comparison between what we wanted on the right here and what we got on the left. And if you look in the distance, the rocky plains looks almost identical to the Gusev Plain. So we nailed it. This is exactly what we were looking for. But you'll also notice that we landed on something entirely different than what you see in the Gusev Plains. There's actually a terrain transition between this really, really flat, smooth stuff that you're seeing right here immediately below the lander and what's off in the distance. So this is actually pretty important and is part of my research. So I'll talk about that in a second. But this is what we actually are sitting on, this really smooth surface. Okay. At this point, so I was at JPL during the landing. I brought 2 Geneseo students who are right here. So this is Alyssa and Megan. Alyssa's from Brighton and Megan's from Canandaigua. And this is Heather, who's a JPL intern, and this is me right here, in case you can't see my face right now. And the reason why I bring this up is what we did when we got there is once we had landed and started taking pictures, we had to pick a place where the instruments would actually go. We couldn't just put them anywhere. They had to be placed in a safe location, free of rocks, on flat surfaces. And so we were part of what's called the Instrument Site Selection Working Group, and I was the head geologist on this group, but there's a ton of engineers in the room as well. And the goal is basically to do like a mini landing site selection process to pick the suitable place for these instruments. And I bring this up because it's actually somewhat historic. That we've never robotically placed instruments on the surface of another planet and just left them there to monitor. That's the first time in planetary history that this has been done. So no one's ever done an instrument site selection process. It was the first time it was organized. The head of the process did a heck of a job arranging it. The only time we did something like this was by the Apollo astronauts. This is Apollo 11, and the Apollo astronauts actually manually took a seismometer and put it on the surface of the moon, manually drilled a heat flow probe, which I think is actually back here, behind, I think this is Buzz Aldrin here, I could be wrong, but the point is that this has never been done robotically before, so it was kind of cool to be part of that process, sort of a first-time process for planetary science. So what we did is it took a bunch of pictures right in front of the landing space and the landing site. We call it the workspace of InSight. And this is basically, imagine the arm reaching out and pointing the camera straight down onto the surface and taking a ton of pictures and making a beautiful image mosaic, which is what you're seeing here. This is the scale here is 10 centimeters, and the resolution of this is 1 millimeter per pixel. So it's really high quality picture. And this is probably the flattest, safest place we could have possibly picked on Mars to place the instruments. The instruments couldn't be placed on steep slopes. They couldn't be placed on rocks bigger than 3 centimeters. And basically the only rock here bigger than 3 centimeters is this little guy right there. All these other ones are small. So this was the easiest job possible. Still took a month to pick the locations. But all the training exercises we did to find a place to put the instruments were much harder than this and took weeks to complete. And when we saw this, we're like, we can go home for Christmas, basically, which the instruments were deployed by Christmas. So let's show that deployment. So this is looking out by the fisheye lens camera again, and there's still some dust now. The dust cover is actually gone. It was removed. It popped off successfully, but some of the dust kind of flopped onto the actual lens, which kind of sucked. But it eventually fell off over time, so it's not so bad anymore. But here is the seismometer being deployed by the arm into the spot we chose. And there it is laying safely on the surface with the engineering tether attached to it. Here comes the windshield. And this is an animation, this one. Okay, just repeating animation. That again is to protect the seismometer from wind. And then incoming from the left, you will see the heat flow probe being put down right there. Okay, so about a meter apart from each other. That's about the scale here. So the deployment was successful. It was really good, and the instrument teams were super excited about that process. Again, it took about a month after landing. This is an amazing picture taken from space by the HiRISE camera. I'm not sure if you guys are familiar with it, but it's basically the highest resolution camera ever sent to Mars. Every pixel on this picture is 25 centimeters in size. So you can see in this picture that this is InSight. There's the two solar panels, one there and one there. You'll see the blast radius from the thrusters all the way around it. It's darker because on Mars, the red color that you see is just dust that settles out of the atmosphere. In some cases, that dust is only microns thick on the surface. Once you blow the red dust away, you expose the basaltic material underneath, and that basaltic material is dark gray. And so the dust is gone, you get the true, what is the true color of Mars, which is the sort of dark gray hue. There's this peculiar white halo around the lander, which honestly, I have no idea what it is. There's still folks trying to figure out whether this is some sort of contamination from the fuel itself, whether there's a layer of brighter material beneath the basalt. We don't actually know what it is, which is kind of cool. But what I think is special about this image is also that you can see the windshield right there. Now, it looks bigger than it really is because I think it's sort of the glare and the saturation from the sun is causing the white shield to look really big. But it's amazing that you can see this sort of meter-sized object from space like that. I just find it unbelievable. Okay, so there's InSight resting safely on Mars. So now to sort of finish this talk, I want to talk about the monitoring phase, which is basically the lander literally just sits there and does nothing. And as long as there's power, I mean, it does stuff, but as long as there's power, we can keep gathering data. So as long as these solar panels still are getting the sun and still storing charge, we'll be okay. Okay, so the first thing I want to talk about very briefly, I'm a geologist, so one of my jobs on the mission is then, once all the instruments are deployed, is to just take pictures of the surrounding terrain and say something about sort of the evolution of the landscape. Like, how does, what does this tell us about Mars? Unfortunately for me, we specifically picked one of the most boring places to land on Mars. And we just wanted a parking lot to put the instruments down. This was not a mission to focus on rivers or life on Mars or any of that stuff. But there's still cool stuff to look at. And in this picture, you can see an impact crater, which is sort of just a couple meters in size, about 19 meters from the lander. We see a sand dune in the distance, about 40 meters away. That tells us that there is loose sand, there is wind, and the wind has been moving, and organizing sand into dunes. Now, what's interesting about this dune, though, if you recall, I just mentioned that the dust of Mars is red, and it's only, in this case, a few microns thick. And beneath that, it's dark gray basaltic material. This dune, if you could go up to it and cut a hole in it, or take a shovel and dig into it, would be dark gray on the inside. This is just the reason why it's white looking like this. It's just the thin coating of dust that's sitting on the surface of that sand dune. And that means that sand dune hasn't been moving. If the sand dune was active and constantly migrating and moving, like most sand dunes do on Earth, then the dust wouldn't have time to accumulate. You would just see dark dunes. But in this case, it means that the sand dune has sat there and hasn't moved and has just collected dust slowly over time. So it's the stuff like that we've been looking at, and also trying to figure out what the materials are made of as well. One of the things that I've been involved with heavily is trying to understand what we landed on in the first place. And as you look at this picture, you'll see, again, there's this really big dichotomy between the surface we landed on and the rockier regolith off to the distance. And so we're like, what exactly did we land on here? Why do we have this sudden sharp, what we call a geologic or terrain contact here, which I've outlined in this yellow line? Well, it turns out InSight landed in what I call a quasi-circular depression. If you look at it from space, it looks like a circular hole, essentially. What it basically is an old degraded impact crater. You're seeing the margin of a really old, we estimate up to about 700 million years to 1 billion years old impact crater that's about 27 meters in diameter. Right now, it's only about 30 centimeters deep. We called it Homestead Hollow. So if you ever see that in the media, that's where we landed. But essentially, what a crater is, on this surface, what happens is the craters are you get a meteor impact, you create a deep hole, and then the crater basically serves as a sand trap. Sand moves across the landscape and gets stuck inside of the crater, and it fills up the crater. And so basically, we're just sitting on, basically, like on a golf course, we're sitting on a sand trap. Most of the material you're seeing down here is sand-sized, wind-blown material that got stuck inside this crater. And these little pebbles and things that you see where my mouse is pointing at here are just pieces of ejecta from nearby impacts that have scattered pebbles across the surface. So we're able to use the diameter of this crater to say that originally this crater must have been 2 to 3 meters deep and has since filled with about 2 to 3 meters of loose sand, which means that probe, the heat flow probe, should be able to get to at least 3 meters by going through just the sand that's filling this crater. So that's super exciting. This is just a montage of pictures of craters in the landing site, going from really fresh impact structures that are deep and have really sharp rims and lots of ejecta coming out of it, to through basically this phase of degradation that takes hundreds of millions of years, going to more and more and more degraded forms until we get to something that's barely recognizable as an impact structure. And that's what InSight landed in, smack in the middle of one of those types of features in the lower right. We call them hollows, and we've seen them at other landing sites like the Spirit landing site. Okay. Oh, by the way, in this picture, you actually see sort of the activity of the sand moving into the crater. So if you look at the fresh example in the upper left, these little white objects that you see here with the shadows in this black and white image, these are sand dunes moving across the surface. Again, they're kind of bright here because they're stable and they're covered in dust at this point, just like you saw in that previous example. And then you see in this other one, they're sort of collecting now up against the rim and getting even bigger and bigger. And they're getting inside of the crater, and you can see some of them in this picture as well, sort of accumulating in the crater. Okay, talking about wind, one of the other interesting results, somewhat mundane, but it's actually important for Mars science, is over the year and a half, we've been looking for any evidence of geologic activity, any evidence of change in the landscape. And it just gives you a sense of how little Mars changes, how basically not Earth like it is today. These little animations you're seeing are showing little grains rolling across the surface, and in some cases hopping across the surface. And this is evidence of the wind actually becoming strong enough to cause sand grains and pebbles to move ever so slightly. And these pictures you're seeing of these moving grains, this is basically all we've seen in a year and a half of change in the landing site. So it's really, really, really slow surface processes going on. Not Earth-like at all. This is classic Mars. Things change today on Mars very slowly. It takes millions and millions of years, hundreds of millions of years, to actually fill one of those craters with sand because the rate of motion of sand is incredibly low. This picture in the lower right, you see time between, you see these streaks, these black streaks. This is a particle that must have hopped and struck the footpad here and removed a little bit of the dust coating to expose the darker paint underneath, which I just think is kind of cool. In the upper right corner here, we have, and I'm just double checking my time. Here we go. Okay. On the upper right here, we have just some wind data. So we've measured winds up to about 14 to 16 meters per second and actually have measured them even higher in this location. So the winds are clearly fast enough to move materials. Okay, now getting to some of the main stuff here. So the Mars quakes. So we've discovered that Mars does in fact have quakes. That's actually a very big discovery that's never been known, but Mars is seismically active. The upper two seismograms you see here are Mars quakes, and they're examples of the best, strongest ones that we've detected. So at the very top is actually the strongest one that's been detected. This is the Sol 235 event. So 235 days into the mission, the seismometer detected a magnitude 3.6 earthquake on the Richter scale. So similar to Earth, we use the Richter scale here. And that's the strongest quake we've detected so far. there's been a notable lack of larger magnitude quakes. The papers that preceded landing predicted that there should be at least one magnitude 5 by now, but we haven't seen it. And of course, you just need more time to detect those types of things. It's just probability at this point. But what you'll notice in this quake, this is the best example of an obvious P and S wave that we saw on Mars. This is one of the best ones that had the most distinct P and S wave arrivals of any of the quakes so far seen. So that's why I show it here. This one is a little less distinct, but the S wave starts roughly in this area, and the P wave starts in this area, and this is a magnitude 3.2. And you can get at the distance of how far the epicenter is. So in this case, it's 1,500 kilometers away from the lander that this magnitude 3.6 was detected. This is just, below is just a comparison to quakes on Earth that are similar distance away, but in this case, much stronger quakes, 6.5s and 6.3s. So I think that's a pretty cool result. And we didn't know that we would even see quakes, although most geologists would have thought that there would be some. But here's some great examples here. What I think is really cool, though, is where the quakes are coming from. So this is a map of Mars on the left. Let me explain this picture because it's kind of weird. You can see the longitude at the top, the latitude on the side here. The color code is elevation. So the high elevations are things in red and orange, and the low elevations are things in like purple and blue. And inside is this little triangle right here. That's where we are, kind of at the equator. And we're inside this big box here. So we're going to look at this box and zoom in a little bit closer. So here's InSight. And you guys probably learned, if you took an intro geology class or if you are a geologist, that from the P and S waves you can get the distance to the epicenter. Now normally you would need at least 3 seismometers to triangulate the exact location of the epicenter, but new technology in seismology, nowadays you only need 1 seismic station to get the rough location of the epicenter, and they use the polarity, and I don't fully understand this, but the polarity of the seismic wave can tell you what direction it's coming from specifically, what compass direction it's coming from in the crust. And so they're using that polarity model to basically figure out where the quakes happened. And the strongest quakes that we've seen by InSight are all in one area. They're not just randomly distributed around the planet. They're actually all coming from this area called Cerberus Fossae. Now, if there's one place on Mars where I would have guessed or predicted that there would be quakes, this is exactly the spot that I would have predicted. And I'll show you why in a minute. But that's where they're coming from. It's a series of cracks and fractures in the crust, and it's not far from the Elysium Mons volcanic complex, which is a giant shield volcano just northeast of InSight. This shield volcano also is associated with the youngest lava flows that we've ever seen on Mars. They're lava flows that seem to be only a couple 100 million years old, based on the crater density on top of them. So this is probably the most geologically active in terms of tectonics and volcanics of any place else on Mars, and we happen to be very close to it, so it's perfect. So let me show you a picture of Cerberus Fossae. This is an orbital picture of Cerberus Fossae, and it's gorgeous. It's this giant fracture that stretches right across the landscape. The width of this entire image is 60 kilometers. And so you can see it's a very well-defined fracture, very sharp edges to it. So it's young, in other words. Here's an older fracture that's right through here, but this one is very young. And these are basically just extensional cracks in the crust. The cracks just basically, the crust is pulling apart here, and it's creating these fractures. There's some places where we see evidence that lava has come out of these fractures a couple 100 million years ago. There's even places where it looks like groundwater may have erupted out of some of these fractures, almost like geysers. And so it makes total sense to me that this would be the place where we would see evidence of quakes on Mars. I just think it's pretty awesome. Okay, getting at the seismicity story now. This is a chart from the Bannert et al. Paper that sort of relates Mars to the moon and to Earth in terms of how many quakes happen. So on the x-axis is magnitude of the quakes from magnitude 2 to magnitude 6. Okay, you can see that there. So that's Richter scale. On the y-axis is the cumulative number of quakes that happen per Earth year. Okay, so it's a cumulative plot. Basically, it's showing how many quakes have happened per year. If we look at the moon, that has no plates, no plate tectonics, and is a very small planet that died very early in its history, the Apollo mission detected very few quakes. So it follows this line right here. The biggest quake detected was a magnitude 4, and there's a bunch of magnitude 2.5s, but it's very low on this chart, very low number. If you look at Earth globally, if Earth, the data, if you plotted it on here, it'd be a huge cloud, but if you plotted Earth on here, it'd follow this trend line right there. Earth is very tectonically active due to plate tectonics. There's hundreds of magnitude 6 quakes every year, or magnitude 5s, I should say. Now, if you look at Earth in some of the quietest regions, so some of these sort of intraplate regions like Geneseo, Western New York, for example, maybe the middle of Iowa, places like that, the quietest places on Earth tend to follow this line right here. So if we look at the Mars example, for the year and a half that we've been there, if we look at the 13 biggest and best and well-defined events on Mars, the ones that were absolutely 100% positive that these are seismic events, those 13 events plot here, somewhere between the moon and the quietest place on Earth. That's kind of where we would have predicted it. This Mars model is actually where it was predicted to be before landing. Now, there have been hundreds of other seismic events, though. We believe they're tectonic events, that they're not from an impact creating an earthquake, for example, or Marsquake. Some of them are really strange. Some of them are high frequency. We don't really know what's causing them. They may be deep quakes that are happening in the upper mantle or something. But there's hundreds of those, and if we include those in the plot, we actually plot a little bit higher than the Mars model. But so this little area in sort of orange or whatever color this is would be the most liberal definition of a quake on Mars, and the 13 events is the most conservative. So we're somewhere in between there, probably. So fits the model quite well, actually. But I don't have any interior models yet. That they're still holding on to those, the geophysicists. I have seen some estimates of the thickness of the lithosphere, but the problem is we haven't had any really big quakes yet to really get at some of the deeper data that we need for things like the core. So hopefully, as we sit there a little bit longer, we'll start getting some of that data filled in. All right, so one of the last things, pretty much the last thing I want to talk about is the saga of the heat flow probe. So I don't know if you guys have been following this, if you're familiar with this, but the heat flow probe has been having some troubles. This is a picture taken in February of 2018, right after the heat flow probe was deployed. You're looking straight down on it, so the mole is sort of inside of here, and when we started the percussive hammering, what we noticed immediately that started to happen, it went down about 30 centimeters, and it went down really fast. It didn't take a lot of time to get in, which is consistent with the sandy surface that you see here. But all of a sudden, the entire apparatus started shaking and hopping around. So you'll see sort of the footprints here from the apparatus has actually shows that it's slid and it's moved. It wasn't supposed to do that during digging or during hammering. So everyone's initial thought was, oh crap, we hit a rock. There must be a buried rock that this thing can't go around. And it was designed to go around like 10 centimeter sized rocks, but it couldn't go around meter sized rocks. So people were pretty pessimistic that we just hit something that we can't get around. So the team decided to pick up the apparatus and reveal the hole to try to see what's happening. And so these are the pictures from that. So it took actually several months. You see this last picture is February 2018. This says October 2019. So this goes all the way around almost a year to where we're still trying to diagnose what the heck is going on. And this is the picture you see. So the mole is sticking out of the hole just a little bit. And we'll notice that it carved out kind of this big hole. And again, sort of like, did it hit a rock? Is it just sort of hopping around and carving out a hole? The mole team and the geologists thought that was unlikely, that there'd be a big rock sitting inside of this crater. What seemed more likely was something that we were a little bit surprised by, is that the sandy soil that you're seeing here, and you'll see if you look at the walls of it right here, where my cursor is and here, it's holding a really steep slope, almost like a perfectly 90-degree shaft. The shaft isn't collapsing in on itself like it does when they tested it through loose material. What we think is going on here, what we're actually pretty positive is going on here based on other observations, is that the sand is actually cemented here. There's a relatively weak cement holding the sand together, and that the walls of the hole aren't collapsing in on the mole as it's going down. Now, the reason why that is important is the mole is designed to use the friction of the hole itself to sort of push off of. And as it goes down, the hole collapses inward on top of the mole, and it has something to push off of as it hammers down into the surface. So it needs to stay coupled with the walls of the hole, and it needs to collapse inward. And they tested this in the test bed, and they tested the cemented soils, and they knew that that would happen in cemented soils. But, you know, what do? You don't really know if those soils would be cemented or not. There is actually some extra information here. If we look at pictures from beneath the lander, this is a picture taken, they reached the arm underneath, and this is actually a blast pit created by one of the thrusters upon descent. And the same sort of principle here, if you look at the sandy soil, you'll notice it's kind of got it's holding like steep little slopes. This pit's pretty steep. And these chunks are not rocks, they're clods of cemented soil. Now, it's a weak cement. If you picked up the clod, or if you bump the clod with the arm, it just breaks into pieces. It's not a very strong one, but it's strong enough that the mole hole wasn't collapsing in on itself. Now, the reason why we think this is happening is because of the idea that this is a sand trap. This crater that we landed in, okay, so I'm not going to tab back, but the crater we landed in is predicted to be about, not predicted, but we did a study of the size of it and the distribution of the craters of that size, and we did an analysis of how long it takes craters to degrade that to this size, and determined that the crater is about 1 billion years old. That means that the infill inside of the crater that started to fill it in, that happens relatively early in the crater's lifespan. It becomes a sand trap. The sand moves in pretty quickly, just a couple 100 million years. It fills it up. And so we estimate that the sand has been sitting in this crater just doing absolutely nothing for about 500 million years, about 500 million years. This soil has been stable, sitting exposed to the surface, exposed to the atmosphere. And the model is that over 500 million years of just sitting there, vapor from the atmosphere, there is a little bit of water vapor in the atmosphere, diffused into the soil and helped create essentially what's called a sulfate cement, or a salty cement. We call it a duracrust, and we've actually seen duracrusts at every single landing site on Mars. We've just never landed in a place where the duracrust was centimeters thick, at least in this case, 1 to maybe even 10 centimeters thick. Okay, so that's kind of unfortunate. We landed in an area of really stable soil that just absorbed all this water over 500 million years, and it became sticky, essentially. So how do you fix that? So in October 2019, they got the idea saying, if we need friction to push off of, let's take the scoop and the arm and apply pressure to the side of the mole. And that will allow the mole, give the mole something to push off of. And sure enough, once they did that, it started to resume its penetration into the surface. That tells us right there that there wasn't a rock at all. Once you pinned it, it started to keep going. This is a picture from this month, okay, July 2020. This is where we're at. So this has been a long saga. It's taken a lot of work to try to figure out what's going on. But right now, the mole is pinned underneath the scoop. The scoop is applying pressure to the head of the mole, and the head is trying to push down. So the mole right now is fully buried in the soil, but it still is not, it hasn't gone down much lower than the surface. And in fact, this particular picture, this is another animation, has us worried. We think the mole is starting to hop back up again, and it's kind of hitting the bottom of the scoop, and you can see the sand inside shaking around. So we think the mole might be having trouble penetrating again. At its current depth, likely due to the same reasons. So the next thing is to pull the scoop away, fill in the mole hole, and cover the mole completely with the loose sand on top. We're hoping that once we get beneath the duracrust, that the soils will start to maybe become less cohesive, less cemented. Okay. The very last thing is, as I mentioned before, pay attention to the quality of that picture of the solar panel. This is the ultimate issue with any solar-driven mission to Mars, is that the dust eventually covers the solar panel and could potentially threaten the power distribution of the lander. And so this is just flashing between Sol 100 and Sol 578, which is just this month. And you'll notice significant dust cover on the solar panel. So power is becoming an issue. So we're starting to think about non-essential instruments that could be shut down. But it's not such an issue that we have to talk about the mission ending. There's plenty of power for the primary instruments and the primary operations going forward. And we're hoping, like other solar-powered missions to Mars, like the Opportunity rover and Spirit, that wind events and dust devils could actually, just by chance, go across the solar panels and completely clean them off. That's what happened to those two rovers, and that's why those two rovers were able to last for years on Mars without losing power. So we're really hoping and planning for that kind of solar cleaning event to happen here soon. And that is a picture of the sunset taken by InSight across Elysium Planitia. And with that, I'll take any questions. Hopefully you're still with me. It's hard to tell. I'm going to minimize this. Get my face back here. And just stay tuned. I mean, this is one of those missions, it's a slow burn. It just, data just keeps trickling out, and papers keep coming out, and you'll see some press releases on occasion. Probably the next time there's a really big quake, you'll see a press release. I will stop sharing my screen so you don't see this weird thing here. There we go. So I'd be happy to take any questions. I don't know, Mark, how you want to do this.
So we can go down through the chat here.
Oh, okay.
Andy says, first of all, there's a thank you from Michael Richard for the update on the probe saga. Yeah, because we were kind of in the dark on that.
It's an endless saga.
Andy Chapman asks, how much of the difference between the solar panel before after photos might be due to angle of the sunlight in each photo?
Oh, sure. Yeah, that does absolutely matter. There's a couple of people who are responsible for monitoring the dust, both in the atmosphere and on the surface. We take regular atmospheric measurements to get the opacity of the atmosphere. So while the images, there's certainly effective lighting, they try to take those solar panel pictures at about the same time of a day with the same illumination to make sure, that we're getting like you said, a good picture. But the dust, the atmosphere opacity is what we really keep track of, because as you guys might know, Mars goes through dust storm seasons, dust storm cycles. Every southern hemisphere summer, the dust picks up in the atmosphere, and we are actually approaching that season right now. And so if there's a really, really, really big dust storm, that could spell doom for InSight, just like it did for Opportunity. That's why Opportunity died. They went through that massive dust storm. But yeah.
Jeff Carr asks, it sounds like your larger quakes were around the fault.
Yeah.
Were there more numerous quakes distributed around the planet? Were they also from around the fault?
Yeah, I really didn't. I actually haven't seen a full map showing the total distribution of all of the earthquakes that have happened. And the reason for that is that you really need a good PNS wave, detectable PNS waves to do that. So there's really only 13 of those events where we can really get the location. Those 13 events are coming from Cerberus Fossae. So the smaller events, which don't have really obvious PNS wave arrivals, they're there, but they're buried beneath the noise a little bit. We know approximate distances, but we don't know exactly where they are. I've heard people talk about, the seismologists talk about these high frequency events that we're seeing on the moon as well, that may be related to really deep-seated mantle processes. In which case, that's just everywhere, right? That's everywhere on the planet.
Bill S. asks, can you talk a bit about the magnitude of quakes? is the scale normalized to enable comparisons between the planets?
It is. I couldn't tell you the math behind it because I'm not a seismologist. I do know that it is. I remember them talking about it, and that plot that you saw there is normalized for direct magnitude comparison. So that's a really good point, and it's absolutely true. I would direct you to the Bannert et al. Paper. There's also Philippe Lagonier is the PI. He's from Geneseo in France. He wrote a paper about the entire instrument and all the processing. So really, I would take a look at those papers to get the exact models. These are great questions.
I got a couple more questions
Sure.
typing. Okay. So Spelunke asks, why doesn't the solar panel have a blower or fans in case of a storm?
I get that question every time, and I don't know why. It seems like it would make some sense, doesn't it? It's power, I think.
Is it possible that you could fold them back up and open them up, and that would kind of clean them up a little bit?
I think the engineers would really be scared of doing that in case they don't open, because part of the issue is one of the big issues, of course, is the temperature of the lander. It's going through some pretty massive thermal cycles, and so the mechanisms stop working, like the actual mechanical parts. So they try to limit as many mechanical parts on these landers and rovers as possible. The mechanical parts that do function every day, a lot of the power has to be given to those parts to keep them warm. So right now there's this huge debate about when do we retire the arm. Right now that deployment arm is being heated so it can still work. And that takes a lot of power, and that power is being taken away from other places. We'd like to retire the arm, but the arm's being used to try to help the heat flow probe, right? Try to keep the heat flow probe working. But it's not endless. So I imagine, this is just my thinking based on what I've heard from engineers, is that blowers or windshield wiper type things, which I've thought about too, all of that requires not only power but mechanical parts that don't operate particularly well in the Mars thermal environment. That's not to say that they shouldn't be doing it, because clearly someone will come up with some sort of efficient system. But what I think they've done instead is the Perseverance rover and the Curiosity rover just work on nuclear power now. So you can get around the whole solar thing altogether.
Is any suboptimal heat probe data being collected?
Yeah, Jeff. So it is working. The heat flow probe is working, and it is detecting, or it is measuring temperature. The problem has been up to just this month is that you saw the end, the butt was sticking out. And so the daily surface environment and the temperature environment, along with all the instruments sort of around it, are affecting very strongly any measurements that would be taken of the soil. What has to happen is the entire probe and some of that tether needs to be fully buried in the soil to start really getting at. And some of the things they can get right now, or what they can get soon, will be the temperature of the soil, which will give us what's called the thermal conductivity of the soil, which will help us understand the porosity of the soil and some of the other properties of the soil that we've never done before on Mars. We don't have any of those measurements. So it's very likely we'll get some very basic thermal physical data in soil properties, but I'm personally getting pessimistic about the 3 to 5 meters, but if they can fill the hole in, and I say all this like this is only being tested on Mars. This stuff is being tested back at JPL and in Germany. They're recreating these conditions. And so every time something is done on Mars, it's done first on Earth to demonstrate that it could work. And the second that they demonstrate that it can't work is the second that they will defund that instrument and shut the arm off, I think. So far, it looks like all of these pathways are working.
Is there a better time of day to have the probe pounding its way down than another time of day?
They want it to work all day, obviously. The pounding of the day, I think the better time of day would only be better for whatever engineers were involved in the process. I don't think it would have anything to do with like the thermal environment necessarily. I actually see the question by Jeff there, a follow-up, can the arm create a small mound? That's kind of precisely what we're doing next. That's kind of exactly it, Jeff, is that this is a funny story. NASA initially told us, JPL in particular, told us that once the heat flow probe was down and the seismometer was down, the engineers said, we will never use the scoop on this lander. They were afraid of going down and scraping the surface of the soil because they thought maybe it would bump one of the instruments and knock it over or break something, right? Because the geologists like me, we were like, oh, can you dig a big trench so we could get a soil profile and do some sort of science from that? And they said, no, we're never going to use the scoop. But now they're going to literally make a hole, pick up some sand and drop it in the hole to bury the mole, and then keep the pressure from the scoop on top of that pile, that mound, as you say, Jeff, and try to give it that sort of resistance to push off of, and also try to fill in, you know, the region around the probe to give it some friction as well. And they're hoping that just by doing this, that it'll eventually reach a layer where maybe it'll be less cohesive and it can work on its own. Because so far, there's no rocks. It's just all about the cohesion of the soil. That's a great question.
What's the lifespan of this probe? Or what's the anticipated lifespan?
Yeah. So the answer I get for that from the engineers is as long as it'll last. So as long as it has power, this is why the solar panel power situation is critical. They'll just leave it. And the other thing is, to be fair, is NASA also has to fund it, because even though it's just sitting there monitoring, there's still staff, right, to do the monitoring, to gather the data, to get it and to process it and to get it in a working form for the scientists. We're still taking pictures every day, still monitoring activity. So all of that costs, you know, a couple million a year, whatever the budget is. So long as NASA is willing to fund it, and as long as there's power, it'll stay. I think everyone was sort of counting on that dust clearing event to happen, because I didn't have time to put this in the talk, but we have seen evidence that dust devils, which are those little pressure vortices you see in deserts, or even on a day, like a day with a lot of snow here, you get little vortices that pick up the snow. We've seen evidence that those have gone across the landing site. There's streaks that have been created by these dust devils that have picked up sand. If one of those can just go over the solar panels, pick up some of that dust, we might get a cleaning event like we saw at Spirit and Opportunity. I mean, that was key. Those rovers were only designed to go for 90 days, and those dust clearing events just kept them alive for years. So hopefully for years. Yeah.
Hopefully.
Yeah. We just need time to get those big events. I mean, that's just a matter of needing that time.
I see a couple people are typing. So
Yeah. Give them a second. The probability models for, if you follow that function of all of the earthquakes or Mars quakes that have happened, it tells you there has to be bigger quakes if you project that out, but they're incredibly rare. So, you know, the question is, when will that happen? I see Bill's question, international participation. Absolutely. This mission is huge for that, because the two primary instruments were built by international partners. So DLR in Germany, and I don't remember exactly, Deutsch something. They built the heat flow probe. They built and tested it and funded it. The French space agency, CNES, built and tested the seismometer. So those are their instruments. Imperial College in London, so the British Space Agency, built one of the sensors on the seismometer, the broadband sensor. There's some participation from, I believe, Switzerland, Spain, just on other things. But the actual spacecraft itself was built by Lockheed Martin through NASA, a contract with NASA. So we built, the U.S. built the actual spacecraft and launched it, and they built the instruments. So ton of collaboration. That's how most of these missions are going these days too. That's how we can afford them.
That's right.
So I'm looking, how many people do we have on here? We got quite a few. It's a good turnout.
I think we were up to close to, I think we were up to 49 at one point. So
Nice. So I see from Tony, what do you think we'll find when more Mars impacts are observed and we get data on the Martian interior? Yeah. So Tony, well, you mentioned actually a couple things here. Impact events. So meteors coming down and smacking into Mars. We actually haven't detected well, I'm sure we've detected some shaking from one of those impact events, but we haven't been able to confirm it yet. There's a team that is trying to tie any quake that we see to possible impact craters, like actual things that you could see on the surface. There's this whole group of people who are monitoring every single picture, looking for change in the landscape, looking for impacts. And so nothing has been confirmed yet on that regard. But in terms of interior, from some of the models, I suspect that Mars will have a thicker lithosphere than the Earth, and I think that's coming out now. I think it'll have a inner core that is similar in proportion and size to Earth, but is not liquid in any way. Solid to the core, essentially, and that bears out with the lack of the magnetic field. There's we don't know anything about the composition of the core, which some people are going to model from it. Some people think the core of Mars actually has less iron in it than ours does, that it's actually more of an iron sulfur core. A little bit more lighter elements in the Martian core. So I suspect to see something like that, but again, it's all we're still at the sort of modeling stage, and we lack some of that key data. The lithosphere thickness stuff, I think, is coming out pretty soon, though. So I would stay tuned for that. In fact, there's a team meeting next week. It's our big annual science meeting. If we had this presentation 2 weeks from now, I probably would have had some new stuff to talk about. But
yeah, cool. We'll have to have you back.
Yeah,
sooner than 6 years.
Sure, yeah. Well, that worked kind of nice, though. It's like I talked about landing site, and then here's the mission. So it worked. I am working on Mars 2020. Well, I call it Mars 2020, but Perseverance rover, which is landing in Jezero crater next year. I'm doing some research on that as well. So if to switch gears from Insight, I could talk about some of that sometime.
That would be fantastic.
Yeah, it'd be nice to see that. Yeah, it'd be nice to see that land first, and then there'd be more to talk about there too.
Sure. Cool. Any other questions for Nick? Just typing something.
Yeah. I'm excited to try to go look at this comet. I saw it the other day and during the morning, and I'm going to try to get out tonight. Let's see.
Yep. So looking to the northwest, you probably only have, we have trees around us, so it's about tilt till about 10:30 was when I was able to see it last night.
Yeah, I have to walk a bit to get out to a field to see it, but I definitely plan to. I see Jeff is asking about a sizable asteroid or comet impact. How do data collection from quakes? Yes, Jeff, I would say that if there was an impact event of the scale of even 100-meter size impact crater, that would provide an amazing data set, especially if it was on the other side of the planet. Because number one, we'd be able to tell exactly where the source was, right? So one of the keys in seismology is you have to figure out where the quake happened. Well, with an impact event, it happened right there. And if it was big enough, something that created a 100-meter scale crater or larger, maybe kilometer-sized crater, you better believe they're going to get some data from that. Now, the quake would look a little bit different. It doesn't have the same sort of PS wave type. There's a slightly different texture, if you want to call it, to the seismograph, but it's still useful data. The problem with that is that impacts of that size are incredibly rare. Usually the new craters that we see that are detected are meter size, and oftentimes they're also broken up into little crater clusters, because there's just enough Mars atmosphere that those meter-size bodies that come in will split into pieces. They'll break up and they'll create this like scattershot shotgun blast of craters. We can see those all the time, but they're not big enough. If they're far enough away, we can't detect the quakes. They have to literally be like right next to the lander in some cases to see. But there's a whole team just waiting to see something like that.
Interesting.
Yeah.
Well, here's some suggestions. Heading down, Bob Easterly, number 2, is heading down to Webster Park with Joe Altieri to see the comet in just a minute. And Pete Bono says he might see it from his backyard. If it's high enough, it's got to get darker. You might be able to see it now, Pete, with binoculars. It's dark enough. It's dark enough to see it.
Yeah, I'm in Honeoye, so I look kind of towards. It's unfortunate that it's kind of towards Rochester, but
yeah, you go up to Harriet Hollister, maybe you'll see it over there.
That's what I need to do.
Yeah.
Yep.
All right. Any other questions for Nick? Well, Nick, thank you so much.
Yeah.
Appreciate your coming on. And even though we weren't able to give you a nice sky tour in person, maybe we could do this another time. And
I would have loved that. I just bought my own. I've got a Celestron downstairs. I wish I could tell you all the specs on it. It's like 9.5 inches, but it's pretty good. But I'm going to go out tonight and do some stuff. So.
All right. Well, you may have missed in our earlier part of the meeting. We are meeting out at our site tomorrow, observing social distancing and getting the bathroom set up for use. If you'd like to join us, I'll send you the what we're going to be doing. You want to set up your scope and take a look on there with us.
Sure. You guys have the place. Where was it? It's not far from me, actually.
It's in Ionia. In West Bloomfield. Yeah. I'll send you an email on all the instructions where we are and what kind of rules we're observing to do this.
Okay, I'm supposed to do something else tomorrow, but I'd rather do that.
Well, I don't want to. You're going to have like a reunion or something. Yeah. Oh, okay.
No, the reunion was canceled. Oh, that whole thing was canceled. Yeah.
I don't want to get you. I don't want to be blamed for getting you in trouble with
your
wife, though.
Yeah, sure. Yeah, absolutely. All right, guys.
Well, thanks so much. Appreciate it.
Thank you so much. Have a good one, everyone.
Take care, Nick.
Bye.
Bye-bye. If anybody else wants to put on your camera and socialize a bit, you're welcome to do so. I'll keep this open for a little while. And if people want to do it, if not, then we can go out and try to observe the comet from wherever we are. So. Thanks for sitting in, everyone. And thanks for coming. Nick did a nice job. It was a lot of fun.
Mark, I have a question for the group. If anybody knows, does anybody know about the old device from 20 years ago, the Celestron Sky Scout? My next door neighbor has that somebody gave him 20 years ago, and that person is now deceased, and he's trying to get this thing working. And I can get it to pick up the latitude and longitude from GPS, but not the date. And even if I try to set it manually, I can't get it past 2015. Is there anything I can do? Does anybody know?
I happen to have one. I might even have the instruction books with it. Did you have the instructions with it?
Yes, and I mean, it's like the simplified instruction sheet. There's a CD in there too that I have not yet opened.
Yeah, I have one, but I haven't used it in close to 20 years.
Yeah. I wonder if the software just will not put the date past 2015.
That's kind of odd. I'll take a look at what I have.
Okay. All right. Thanks.
No problem. All right, I'm gonna stop the recording. I want to stop the recording. How